Hello everyone. Here is our next question in computer organization from the topic instruction pipelining. This question was asked in the year 2007 for 2 marks. The question is, consider a pipeline processor with following 4 stages: instruction fetch, instruction decode and operand fetch, execute and write back. The instruction fetch, instruction decode and operand fetch and write back stages take 1 clock cycle each to complete the operation. The number of clock cycles for the execute stage depends on the instruction. The add and subtract instructions need 1 clock cycle and the multiply instruction needs 3 clock cycles in the execute stage. Operand forwarding is used in the pipeline processor. What is the number of clock cycles taken to complete the following sequence of instructions? First instruction is add R2, R1, R0, which means the values of R1 and R0s are added up and stored in R2. Multiply R4, R3, R2, which means the values of R3 and R2 are multiplied and the result is stored in R4. Third instruction is subtract R6, R5, R4, which means the value of register R4 is subtracted from value of register R5 and the result is stored back in register R6. So to attempt this question, first of all we need to find if there is some data dependency between instructions or not. So see, the second instruction, it is dependent upon first instruction for the value of R2 because the first instruction is producing the value of R2 which is consumed by the second instruction for this arithmetic operation. So the second instruction is dependent upon first instruction. Similarly, the value of R4 is consumed by third instruction which is getting produced by the second instruction. So third instruction is also dependent upon second instruction. Till the new value of R4 is available, the third instruction cannot proceed for completion, right? Similarly, till the new value of R2 is produced by the first instruction, the second instruction cannot proceed to completion, right? So we need to find the number of clock cycles that would be required to complete these 3 instructions using operand forwarding. But let us step back a little bit and first of all see if operand forwarding is not used, then how many clock cycles would be required, and after that we would proceed forward to using operand forwarding, right? So let me draw the clock cycle diagram for the case where we are not using operand forwarding. So without operand forwarding, the clock cycle diagram would like this. Let's say this is clock cycle 1, then clock cycle 2, clock cycle 3, like that. These are the clock cycles. So let us draw 12 clock cycles, and after that the first instruction can be scheduled in first 4 clock cycles because execute of this would take a single clock cycle, as it is given that add and subtract instruction would need 1 clock cycle, whereas multiply instruction would need 3 clock cycles in execute stage. All other stages would take 1 clock cycle each, right? So all the 4 stages of the first instruction can be scheduled in first 4 clock cycles. So instruction fetch of instruction 1 followed with instruction decode and operand fetch followed with execute stage followed with write back. So in the first 4 clock cycles the first instruction would get completed. Now the next instruction fetch can be scheduled at C2, right? So when instruction decode and operand fetch of I1 is progressing, parallelly we can start instruction fetch of the second instruction. Now what about instruction decode and operand fetch? Instruction decode and operand fetch cannot be scheduled before the register the R2's new value is available in R2, in the register R2. That is, till the write back stage of first instruction is done, is finished, till that point of time we cannot schedule the operand fetch stage of the dependent instruction. In this case, I2 is the dependence instruction. So operand fetch has to be scheduled after the write back is done, because after write back only the new value of R2 would be available in R2, right? So there would be two stall cycles here where we would do nothing, and after that we can schedule the instruction decode and operand fetch stage. So note here, had this stage been divided into two parts, instruction decode separate and operand fetch would have been a separate stage, then we would have required only operand fetch to be scheduled after write back. Instruction decode could have happened before it. As it is a combined stage where operand fetch is merged with instruction decode, so because we need to schedule operand fetch after write back is done, we are scheduling this combined state after write back of the first instruction, that is the producer instruction of R2, right? After instruction decode is done, now execute can be scheduled for the second instruction, and as you can see that multiply instruction would require 3 clock cycles for execute stage. So here we would need 3 clock cycles. Execute would start in C6, then C7, and then it would finish in C8, followed with write back stage. So in C9 we would complete the second instruction. Now coming to third instruction, it is also dependent upon the previous instruction. Instruction fetch of I3 can be scheduled in the C3 clock cycle, and then as it is dependent upon second instruction, the operand fetch of the third instruction cannot be scheduled before write back of the second instruction, because the new value of R4 would be available in R4 only after write back stage of second instruction is completed. So only after C9 we can actually schedule the ID stage, that is instruction decode and operand fetch of the third instruction here, right? And all these cycles, third instruction would just be waiting. So these are all stall cycles, and after that in C10 we can schedule the operand fetch stage followed with execute stage, and as it is an subtract instruction, it would need only 1 clock cycle in execute stage followed with write back. So without operand forwarding, the number of clock cycles those would be required is 12 clock cycles. Now see, we need to find out number of clock cycles when operand forwarding is used. So what is operand forwarding and how many clock cycles would it require? So for answering this question, we need to first find out the point of production of the data value by the producer instruction and the point of consumption of this data value by the consumer instruction. So see, the value on which the second instruction is dependent is the value of R2, and the value of R2, the new value of R2 is produced after the execution stage, that is arithmetic logic unit's output actually contains the new value of R2 even before the write back stage is completed. The new value of R2 is actually present over here, that is at the output of arithmetic logic unit. So this is point of production for R2, right? So this is point of production for R2, and point of consumption for this new value of R2 is the input of the second instruction, right? So this is where the new value of R2 is required by the second instruction. So this is point of consumption for the new value of R2. Similarly, the point of production for the new value of R4 is at the output of execution stage of second instruction. So this is point of production for new value of R4 Even before the new value of R4 is written back in the register R4, it is available in this pipeline at the output of arithmetic logic unit. And this is getting consumed by the execute stage of third instruction. So this is point of consumption for the new value of R4. Now using operand forwarding, what can be done is that this point of consumption can be scheduled right after point of production of the dependent data value, right? So point of consumption and point of production can be back to back. It cannot be scheduled before point of production, but right after point of production, the point of consumption can be scheduled. Similarly, in the second and third instruction also, after this point of production of R4, the point of consumption of R4 can be scheduled right after the point of production of R4. So let us now draw the pipeline clock cycle diagram with operand forwarding and find out the number of clock cycles required. So let us designate again the clock cycles with C1, C2, C3, C4, C5, C6. So now the number of clock cycles required would be less. So let us designate this 8 clock cycles with C1, C2, C2 up to C8. Now the instruction fetch of the first instruction can be scheduled at C1 and instruction decode and operand fetch in C2, execute in C3 and write back in C4, same as that of without operand fetch scenario. So there is no change here. Now coming to second instruction, again instruction fetch can be scheduled here, and there is a change in where we can schedule instruction decode and operand fetch. Now the dependency of execute stage is not on the output of instruction decode and operand fetch of the instruction, because we are not taking the input of execute stage of the second instruction from the output of instruction decode. We are rather taking it from output of the execute stage of the first instruction, right? So instruction decode can be scheduled anywhere, so it can be scheduled even in C3. So as in this diagram we have seen that point of production is of R2 is at the output of execute stage, that is here, right? So this is point of production of R2, and so the execute stage at the input of which the point of consumption of R2 is there, it can be scheduled right after it. So actually we didn't have to wait for write back to complete. We can schedule the execute stage of I2 here, because point of consumption of R2 is here, and as point of production is before point of consumption, so execute stage can be scheduled here, right? And after that 2 more cycles would be allocated to execute stage followed with write back. So on C7 the second instruction would get completed. Now point of production of R4 is this at the output of execute stage, right? So I3's instruction fetch can be scheduled in C3. With similar argument we can schedule actually the instruction decode and operand fetch in C4, because anyway wherever we are scheduling this operand fetch, we are not going to use the value of R4 from the output of this stage for the execute stage. We are not going to, the execute stage is not going to use the output of this stage for getting the new value of, for getting the value of R4. It would rather use the output of previous execute stage of previous instruction for the new value of R4, right? So it would directly get forwarded from the output of execute stage of previous instruction to the input of the execute stage of the third instruction. So execute stage of I3 as point of consumption of R4 is at the input of execute stage of I3. so it can be scheduled right after the point of production of new value of R4. So here the execute stage of I3 can be scheduled because point of consumption of R4 is here, and we can schedule the point of consumption right after point of production of this register. Now it is going to take just a single cycle because it is subtract instruction, and after that we can schedule write back, and there would be some stall cycles here. So two clock cycle stall clock cycles would be there. So with operand forwarding we can see we are requiring 8 clock cycles. So hope you have understood the concept of point of production and point of consumption of the dependent value, the value on which the next instruction is dependent. And the rule is point of consumption of the value can be scheduled right after point of production of the producer instruction. And with that we have solved this problem, and we have got the answer as 8 clock cycles. So the option B is correct. Thanks for watching. Bye.